Now, light waves. You all know the light wave has a dual property. Either it will behave as a wave or as a particle. When it behaves as a wave, then it comes under classical theory. When it acts as a particle, that means a photon have a it has a energy in the form of a photon, which is E is equal to h nu. It comes under quantum theory. Now, in the quantum theory, we see it that there is a molecule AB. The electromagnetic wave, they strike the molecule. They give they either give energy to molecule or take energy from the molecule. That means if they give energy to the molecule, the energy of the scattered radiation that decreases and the energy of the molecule increases. When it takes energy from the molecules, then the energy of the molecules decreases and the energy of scattered radiation increase. If there is no change in energy, then the energy of the incident and the scattered radiation that remain the same. This is called Rayleigh scattering. See it. We can explain it by taking one example. There is one tabla. You see it. There is one molecule. When we strike that molecule with some energy, if it is in the rest form, then this tabla will get energy. It will start vibrating. So the energy of the uh, uh, scattered molecule E2 will be less than E1. Why? Because the molecule will gain energy and the energy of incident radiation decreases. When this is the case of when it is in rest form. When it is in motion, your tabla is in motion, already it is vibrating. When you strike it with incident radiation, some radiation of some photon of energy on it, what happens? It gains energy from the vibrating tabla and its energy increase, the energy of scattered radiation increases. In that case, E2 is greater than E1. Now we can show it by an energy diagram. Suppose there is a molecule, the incident radiation strikes that molecules and the molecules will gain energy. It will move to the some higher energy state. This higher energy state is the virtual energy state. It is not a real energy state. After some time, it will the molecule will remain in this state for a very short time. After some time, the molecule will lose energy and will come to the ground state. This type of scattering, there is no gain in energy or loss in energy. The energy remains the same. Such type of collision is called elastic collision, and this is called Rayleigh scattering. Suppose molecule is in the ground state and the electromagnetic radiation, they strike the molecule is excited, gain energy and get excited. It again go to the virtual energy state. Now from the virtual energy state, it comes to it doesn't come to the ground state but go into some other energy state. Suppose it go into even state. So what happened here? The energy of incident radiation is greater than energy of scattered radiation. Here you can see in the diagram. So E1 is greater than E2. Such type of scattering, and we get a lines. These are called stroke lines. Now, when suppose there is a molecule which already having some energy, that is in the energy state E1. When electromagnetic radiation strikes this molecule, it will go to the higher energy state and then come back to the lowest energy state, that is ground state. In this case, the energy of scattered radiation is less than energy of excited state. This is called anti-stroke line. So all is this about quantum. In the quantum chemistry, when Rutherford was working on it, then he says the molecule is moving in a circular motion. In the circular motion, if it moves in a circular motion, so it changes direction. That means its velocity will go on changing. It should not remain, so the spectra obtained should be continuous, but it should be, but the spectra comes in scattered form, not continuous spectra comes. Then Bohr gave its theory, and this is called quantum effect, which proved it is the quantum of energy is a photon and is a quanta of energy, and its energy remains fixed. So it is like this. Now we will come to the wave classical theory of. In wave classical theory, it talk about the polarizability of the molecule. See, in the diagram, I have shown the hydrogen molecule. Suppose we are taking example of a hydrogen molecule. Hydrogen molecule, if it is as shown in figure 1, it is lying, the bond angle is along the direction of the, in the direction of a electric field. So it will create positive and negative field. And second situation we take it, that is the molecular axis is perpendicular to the direction of electric field. When the electric field is applied, when molecule is moving, it form a ellipsoid. Ellipsoid has a shape, have a two axis, minor axis and the major axis. What will happen if the bond axis is along the electric field? The electric field experience will be the more, and there will be, it will affect the bond, and its polarizability will increase rapidly. But in the case of a molecule, when its bond axis is perpendicular, that is at 90-degree angle to the electric field, then what happens? These molecules, these electrons, they will not, they will not, the electron are negatively charged, definitely you know it, they will move toward the positive charge. In the first case, they will easily move toward the positive charge, but in the second case, when it is perpendicular, these molecules will not move towards the positive charge so frequently, because it will not break its bond. So what happened? There are two axes, that is minor axis and the major axis. Always it prefers polarizability, always prefer minor axis, because there are more possibility of polarization of a molecule in it. Now we take a molecule, simply a molecule AB. Now we will talk about the polarizability. Polarizability, oscillatory field, vibration frequency, incident vibration frequency. When we apply the incident energy, we strike the molecule with the electric energy, it's passed through. When it is in the static state, there is no problem. When it is present in the oscillatory field, generally we apply it the electromagnetic radiation, they will produce the oscillatory field. That means the molecule not remain static, and with oscillation of the field, your field changes. Sometimes it is on the left side positive, sometimes it is on the uh, right side, so it's always oscillating here and there. so it will produce vibration also. In this incident vibration frequency, when a molecule is struck with the incident vibration frequency, is it will induce polarizability in the molecule, and that is called induced dipole. Dipole moment will be created, and this is given by mu is equal to alpha E, where alpha is what? It is polarizability. If molecular vibration change the polarizability periodic change, then alpha is equal to alpha naught plus beta sine 2 pi nu vibration T. E is equal to this energy. If it is placed in oscillating electric field, the energy also changes. That is, for static field, E will be nu is equal to alpha E, that is in static field. When we applied the oscillatory electric field, E is equal to E naught sine 2 pi nu T. 2 pi E naught sine 2 pi nu T. So the value of this nu will be induced dipole, that will be equal to alpha E sine 2 pi nu t when the field is static. When we apply the induced field, when the molecule is in the static mode, when the molecule is also moving, it has some vibrational and rotational spectra already oscillating. So there are two type of field now we are applying. That is, we are applying the oscillatory electric field, and the molecule itself is moving. So it will have its own vibrational and rotational frequencies. Suppose, see, it is a AB molecule. They are in such a situation when the molecule moves, its vibrational or rotational energy changes. It vibrates. So it changes position. And position, you see it, I have shown it by arrow. So it becomes, earlier it is in the direction of direction of oscillating electric field. When it moves, it changes direction, and its oscillatory field, its vibration and rotational frequency gradually decreases. And if molecular vibration changes the polarize, it create a polarizability. And if the molecular vibration changing the polarizability in a is a it is a periodic change, that means it is regularly changing. So the polarizability will be, now the induced polarizability will be alpha naught plus beta sine 2 pi nu vibrational T. Beta is rate of change of polarizability. Alpha naught is equilibrium polarizability. Now the induced dipole moment will be the combination of, now mu will be alpha naught plus beta sine 2 pi nu vibration into T plus E0 E naught sine square pi nu T. This is beta is what? It is polarization effect. It is due to the inner motion of the electron. Suppose if the uh, if the oscillating electric field whose frequency is the same at which the molecule vibrate, oscillate, then there is no change in oscillatory frequency of the molecule. It simply oscillate. So in this case, beta will be 0. So the induced dipole moment that comes out to be the same as the incident radiation. So in this case, that is the Rayleigh scattering. If beta is positive or negative, it depends the your this phenomena, that is stroke line and anti-stroke lines are due to the only the factor responsible for it is beta, that is polarizability. Rest you can see in your notes. I have given it to you. I will explain you in notes also what you will do. We will talk rest from the content given by me to you. Okay, thank you.